Right, now we're looking at tangential velocity, and this specifically with the syllabus, this equation here, that's one equation that we can use to do tangential velocity, and of course that's sort of in a way related to angular velocity, and we're going to see that in upcoming videos. But let's talk about tangential velocity because we just talked about the centripetal force equation, and we said that it had tangential velocity in it, so let's talk about what that actually means. Okay, now tangential velocity is a linear velocity that the object has when it's taking a circular path and the velocity tangent to the curve, right? So if we have a hammer thrower here, you can see as she moves around through a complete circle, she has an axis of rotation. She has the string that is attached to the hammer, and of course she feels a tension force. Now that tension force is causing the ball to change its motion and continue in a circular path. If she lets go of the tension force or the string, then that ball will continue in a straight line, and that is where we get the tangential velocity, right? So the centripetal force is going inwards like that, so the centripetal force is equal to the tension force in the string or in the cable, and then we have the tangential force which is coming out here. Now of course discus is the same thing, right? So you can see in the video we've got a discus thrower here. In this instance, that what's causing them to change direction of course is the arm of the discus player, and as they're moving, or athlete, as they're moving around, we're increasing the speed of rotation of the body, and that's also increasing the speed of its tangential velocity. And of course we will see later on that there is a relationship between those two, right? The rotational velocity, right, or the angular velocity is given this symbol there, which looks like a W at that point, but let me just try and do that a little bit better, okay? And that is equal to the tangential velocity times the radius. Well, if the radius is the person's arm, so this is the string here, but in the video we had the person's arm. If that's the radius, that's constant, isn't it? So how else can you get a greater tangential velocity? Well, if you rotate or spin more times or faster in the same second or two, right? So if you increase the rate of rotation. And so basically what I'm saying here, hopefully it makes sense, that as you increase the rate of rotation, you get an increase in the tangential velocity when you release it, because the radius is the same. And we're going to be coming across this more and more, and so make sure you make this link between this and the tangential equation, right, 2 pi r over t, which is what we're going to be looking at in this video. Okay, so here we have a pizza thrower throwing pizza up in the air, and as they do, they spin it, and so the spinning pizza has both rotational velocity and a point on its surface has tangential velocity. And so this point on the pizza here would be having a tangential velocity as the whole pizza rotates. And so there's many examples in physics where we can explore tangential velocity. And so we have orbital velocity, which we're going to be talking about that in, when we talk about the space section. We have points on a wheel or points on a pizza. Okay, we have the hammer throw, which we've already talked about. Car turning a corner, cyclotrons, that's where we get particles and accelerate them really fast in circular trajectories, and we're going to be talking about that in module 7 and module 8. So any point undergoing circular motion, any point undergo circular motion will have a tangential velocity and an angular velocity. So it's important here. Now I've tried to connect multiple modules here, multiple concepts for multiple modules around this idea. So when you put this in your mind map, make sure that you put these examples near this, and maybe even put like an M7, M6, etc. So you know that there's multiple connections between modules. So I've got orbital velocity here, which is of course module 5, we're doing that. Points on a wheel, module 5. Hammer throw, well, we don't really specifically talk about hammer throw, it's just a generic example. Module 5. Cyclotrons, that would be module 7, module 8. Then we can talk about magnetic fields, etc. So put these links in now, and when you do them, go back to here and make those connections stronger, okay? And you can only do that with your mind maps, etc. So make sure you have a look at that. So here is 2 equations we can use to calculate the tangential velocity. Now let's just think about what we're doing here, because we want to make it make sense. Let's look at this equation. The tangential velocity, what is the formula for velocity? What's the general formula we tend to lose? Well, we usually say it is the displacement divided by time, right? The velocity is the change in displacement divided by the time. Okay, well, what is the displacement if this point on this pizza is rotating around this way? Well, the displacement is just the circumference of the circle. The distance it travels is the circumference of the circle. So that's where we get our 2 pi r from, right? So our distance traveled is our 2 pi r. And then the time, well, if we simplify the time and say how long does it take to go around once, then that is the period. And so we can come up with a tangential equation is how far this object travels in one period. And that's the same whether we're talking about orbital velocity, right? How far does this satellite travel around its orbit in one rotation in a certain time? And that can give us its orbital velocity, how fast it's traveling, right? We can also have this relationship here, which we will derive in other videos. But the tangential velocity is equal to its angular velocity times the radius. And we mentioned this equation when we talked about the discus thrower. Okay, and so with these two equations, of course, put them in your equation sheet and you know what units, etc. they have. Now, we haven't talked about angular velocity in radians per second, etc., but we will. So just write it in now, and then when we do the videos on that, it'll sort of make sense. And then come back and have a look at this, your notes on this and your mind map to solidify and make them stronger. So let's do a question on this here, right? We've talked about these, so let's now apply this to a question. It says a hammer thrower rotates a 1.5 kilogram steel ball at 4 hertz before releasing it. Her 97 centimeter arms hold a 1.4 meter steel cable attached to the ball. Calculate the tangential velocity. All right, so straight away you see the key word tangential velocity, so you're highlighting that. Okay, we've got some data here in terms of our numbers, so let's highlight our data, and then we know we have to do something with it, and of course we have to then check the units, etc. Now, what equations do we use? Well, we had two equations from before. This mentions nothing about rotational angular velocity, so we can't use that one because we also haven't talked about it, but we have talked about this one, right? So let's have a look here. Do we know something about the radius here? Well, yes, we do. We were told that her arms were 97 centimeters and that she holds a cable that was 1.4 meters. So we add those two together, but we have to, of course, change the length of her arm into meters. So it is the same unit. And so we do that and we get 2.37 meters. Now, the period of rotation. The period is how long it takes to go around once. We weren't given period here, but we were given the frequency, and you should know the relationship between period and frequency is that. So if I go 1 divided by 4 hertz, then that's telling me I have a period of 0.25. Now, I've got the wrong units in there I just saw, so let's fix that up there. So notice I put in hertz there. It should actually be seconds. And so that now makes sense with our units because we have now meters per second. And so we get 59.6 meters per second. That is her tangential velocity of the ball. If we were to try and use this similar equation, but we know that period is equal to 1 over f. Okay, so if I substitute 1 over f into that equation, then I will get this one here. Okay, and so that means that now I can do the same calculation and I end up with the same answer. Okay, so I've used two different ways to calculate it pretty much to get the same answer. All right, calculate the centripetal acceleration of the ball. So remember, the centripetal acceleration is the acceleration going towards the center there. We know our formula is v squared over r. So what we can do is we can put our tangential velocity, which we just calculated up here, into there. We know the radius is 2.37 meters, and then we get a value for the centripetal acceleration. The tension force she feels as she rotates. So here is where we have to realize that it's the tension force that's causing the ball to change direction, which is the same as the net force, right? So force tension is equal to force centripetal force. We know the formula for centripetal force is mv squared on r, so we can put that in there. Then we just put our values in. Now with this way I've calculated, I've done everything from first principles. I put the velocity in, etc. But I really could have just used that number, because that number is that, right, which is the same as that, right? So I could just get this number and times it by the mass. But we get the same answer, 2,247 newtons. And that makes sense in terms of units, because we know that 1 newton is kilograms meters per second squared. And so we have kilograms meters. Now if I expand this out, right, let me just do it for you, right? So we have meters squared, seconds squared, which is this bit. Divide that by meters, then that cancels, one of those cancels, which gives us meters per second squared. So I encourage you to try and do that, because if you put your units in and you cancel them, that can help you out with understanding what's going on and where we're building our quantities, etc. from. So that's how you do a question with that one. So that's it for this video. We've explored how to use the centripetal force equation. We have looked at what else, right? Doing a little bit of active recall here. What else did we look at in this video? Well, we talked about and revised the centripetal acceleration formula, v squared over r. And then we also looked and defined what tangential velocity is. And it is the velocity that an object has as it's moving around a circle, but it is measured as a tangent to the curve. If you were to cut that force causing it to move, it's the velocity the object would move with, right? It's called the linear velocity as well. We had 2 equations for the tangential velocity. Hopefully you've got them written down in your notes. And one equation we explored here, the 2 pi r over t equation, and we talked about how that came about. And then we used another one, which is we're going to be talking about in later videos when we actually talk about angular velocity. But that was the tangential velocity, was linked to radius and, of course, the angular velocity as well. So we did quite a bit in this video. Make sure you got your notes that are detailed down, and then of course you've got to test your understanding, right? You might have this poster already printed up, so you can do that. We've got cards, there's the formula sheets, and of course you're testing yourself with the questions below and the different ways in which we study. So make sure you check out the study tips and tricks as well. So I'll see you in the next video where we continue to explore circular motion in this section of the syllabus. See you then. And then of course we have just turning a wrench. And so all of those examples are some examples that we have in everyday life where objects undergo circular motion. But for a definition, circular motion is when an object moves in a circular path or along the circumference of a circle in its undergoing circular motion. So it doesn't have to go completely around in a circle like this. It can just turn a corner. So it's going through a circular path. In other words, it's changing direction as a result of a net force. So if we have a look at this tennis ball here, we can see that we've got a string pulling on that tennis ball. And if that string wasn't there, then that tennis ball will keep going in a straight line, according to Newton's first law of inertia, right? Objects that are in motion undergo motion in a straight line unless acted upon by an unbalanced external force, right? So I throw this in space and this keeps going forever in a straight line. If there is a force acting on that object, and if that force, the net force, is unbalanced, then it will start to change direction. And so here we have a string causing it to change direction, and that direction is resulting in circular motion. Now that's uniform circular motion if the object is having the same velocity, right? And so we can see just a quick little video here of something I did before. We're doing a workshop and a party when I act as the crazy scientist. But you can see here a totem tennis where a ball is on the string and it's just flipping around the center pole there. That's circular motion. The string is providing tension force to the ball, causing the ball to change direction. Okay, here are some key fundamental ideas about circular motion. Okay, and make sure you can explain and identify these, because these pop up a lot of the times in multiple choice questions. First thing is that with circular motion, there is a force that acts 90 degrees to the direction of motion. So here is our direction of motion. Okay, but there is a force acting on that object, and that force is 90 degrees to the direction of motion. Okay, and when that occurs, the object changes direction in a circular fashion. The next thing to realize is that force causes the acceleration. Remember from Newton's second law, F equals ma, that when we add up all the forces in a direction, if they're unbalanced, then there is a net force acting on the object, and that net force causes an acceleration to happen. Okay, let's say we have this calculator, right? It's resting on my hand. I'm pushing that way. At the moment, the horizontal forces is me pushing that way, the applied force, and then there's friction acting backwards, right? So they're balanced. However, if I push more now with a greater magnitude, I'm overcoming the friction, which means the net force is causing the calculator to undergo an acceleration, okay? And that's the same with circular motion. And when that acceleration happens, we call it a centripetal acceleration. That is acting towards the center of the circle, and we're going to be learning more about that. So going into the center of the circle is our centripetal acceleration. Another key aspect is the velocity of a ball is constant, then we say we undergo uniform acceleration. Now, if the velocity is constant, how can it undergo acceleration? Because isn't acceleration just the change in velocity divided by time? Well, if it's got the same speed, is its velocity changing? Yes, it is, because its direction is changing. Remember, velocity has a magnitude plus a direction, and the magnitude, that is the speed, might be constant, but the actual direction is changing, so therefore the velocity is changing. So an object going around, let's say a planet going around a central sun, is maintaining a certain speed in its orbit, right? But its direction is constantly changing, so therefore there is acceleration going on. And what do we call that acceleration? Centripetal acceleration. Okay, and so that's something we need to think about as well. Now, there's many types of forces that can cause an object to change the path of its motion and therefore undergo uniform circular motion, and we're going to be looking at those in the next video. So that's a quick introduction of what circular motion is. Hopefully now you should be able to define what circular motion is, that an object is undergoing a change in direction, right, due to the application of a force acting 90 degrees on that object, and that force causes the object to undergo a circular path, like turning a corner, or continue in a complete circle, right? And a complete circle, in this video, we looked at, for example, the Ferris wheel, where you're spinning around in a complete circle. Okay, we had planets orbiting a sun, they were complete circles. And then we had two examples that were just showing a circular path, right? We had a car going around a corner, and we had a wrench tightening a nut. And so all of those were circular motion. You now should be able to explain what we mean by uniform circular motion and some key features. So, as always, make sure that you're in the physics flow, you're constantly focused on the knowledge, and you're revising it actively. And of course, you're seeing the relationships between the videos that we make, between the concepts, and you're doing your flow diagrams. So I'll see you in the next video where we explore more circular motion.